Welcome to this video. I'm Sini from Politecnico di Torino and I would like to present my paper titled Improving Software Reliability with Rust, Implementation from Enhanced Control Flow Checking Methods. My co-authors are Mohammad Reza Solouki and Massimo Violante from Politecnico di Torino e Giorgio di Natale from Team Laboratory of CNRS in Grenoble, France. We can start with the outline of this presentation. First of all, I will provide some motivations on why implement software implementing hardware fault tolerance and why we are targeting the Rust programming language. After that, I will introduce the chosen techniques, commonly referred to in the literature as control flow checking. Then I will describe the experimental campaigns we performed and the proposed approach to perform fault injection by presenting the fault injection manager, the model of the injected faults, and how we classify the injection outcomes. After that, I will show the experimental results and finally describe the conclusion that we are planning for the future. But first of all, why target Rust for implementing software implemented hardware fault tolerance? Rust is a modern programming language that integrates memory and concurrency protection paradigms of the shelf. It guarantees performances similar to C, since almost all the checks are performed by static analysis at compile time. There is, moreover, an increasing interest in adopting Rust to develop embedded application, and there exist on the market certified compilers allowing the development of safety-critical applications by Rust. The portability of the hardware code between different platforms is another motivation to implement the hardening at the high-level programming language. Then, what is the control flow checking? Control flow checking methods are a subset of the software implemented hardware fault tolerance proposed to detect faults that modify the execution flow. A common way for implementing this approach is through signature monitoring, in particular by adding test and set instruction in the source code. The main idea of the control flow checking is the concept of control flow graph, like the one shown in this slide, needed to divide the program code into basic blocks. The basic blocks are maximal sets of ordered instructions that run sequentially from the beginning to the end. A basic block cannot contain branching instructions such as jumps or calls to function, except for its last one. In this paper, we present the results obtained from 6 experimental campaigns. In the first 4, called O0 since without compiler optimizations, we injected n equal 1000 faults. Due to the reduction of instruction numbers thanks to the compiler optimization, it has been possible to inject, before the end of the applications, only 271 faults on the YAC hardened version and only 295 faults on RACFED hardened versions. These 2 latter experiments are indicated as O1. We can start with the proposed approach. In particular, our approach required 4 steps. First of all, the selection of the control flow checking algorithm, then the implementation of the control flow checking in the Rust programming language, then the adaptation of the fault injection manager already published to inject into Rust developed processes, while in the previous version it injects into C developed processes. Then to perform experimental campaigns to evaluate the algorithm effectiveness in hardening an automotive application. In particular, we implemented 2 CFC algorithms to harden our benchmark application. These are YACA and RACFED. The first is based on signatures represented by bit fields, where each bit represents an individual basic block. The second RACFED instead is based on a signature represented by consecutive adding and subtractions of random values defined at compile time. This allows to perform inter-block detection to check that all the instructions within the basic blocks have been executed. Let's now better detail how we performed the experimental campaign. The fault injections are performed thanks to the GDB debugger, while the target is a platform emulated at the instruction set architecture level resulting to QM. In the figure, the elements involved in the fault injections are colored in red. The application source code is compiled thanks to Cargo, which produces a single ELF file containing the application binaries and the memory map. Each fault injection campaign is defined by the number of faults to be injected, the injection target and the adopted fault model, the output symbols to be logged by the debugger, and the control flow checking signature variable, as well as the detection variable. A golden run that is fault-free is performed to get the correct behavior of the application. Then the debugger allows to inject faults. The faults injected during the campaign are permanent sackets affecting a single bit of the core's program counters. Each individual injection is characterized by an injection time, the sacket bit status that can be of course 0 or 1, and the affected bit of the register, that is, in other words, in which position the bit within the registers remains stacked. In the campaign indicated as O0 and O1, we choose randomly as the affected bit position from the 5th to the 13th one, to allow a minimum error of at least 4 instructions, and at the same time to avoid that the program counter exits from the .test area due to the injection, directly raising a trap. But since RACFED provides also intra-block detection capability, so it is capable of detect if an instruction is kept within a basic block, we targeted from the 3rd to the 13th position, allowing to skip only a single instruction. We did this to check the differences, if any, between YACA and RACFED in their diagnostic coverage. The outputs from the applications are stored in log files thanks to GDB, to avoid any instrumentation of the source code. At the end of the injection campaign, a classifier, which classification rules will be described in the following slide, runs on the obtained logs, providing an outcome for each individual injection. In this slide are shown the classification criteria adopted to determine the individual injection outcomes. The classifier is basically a state machine, which progressions is based on the comparison between the logs of the golden run and the considered individual injection log. At the beginning, before the injection, the classifier only checks that the detection mechanism is not triggered, otherwise it leads of course to a false positive. After the injection of the fault happened, the machine moves to the status latent after injection. If at a certain point the output between the fault-free and the fault-affected run diverge, 2 cases are possible. If the fault is detected, we are in presence of a detected by the CFC self-settings, the detection variable, or by an hardware trap, for example when the program counter goes outside the allowed memory range. These 2 cases are indicated as detected by software or detected by hardware. In the case there is a divergence but the fault is not detected, we are in the presence of a wrong behavior of the application, and hence in the residual case. Both the residual and the latent case are subclasses of the undetected. The injection is classified as golden if there is no behavior divergence except for the set of the detection variable. After the individual injection outcomes are determined, it is possible to produce the ISO 26262 compliant campaign results. The ISO 26262 compliant results are obtained thanks to the formulas shown in this slide. N is the number of faults injected during the campaign. Given the results from the individual injection, we can define that safe is the percentage of as golden outcomes over all the injections. Detected is the percentage of injected faults detected by the control flow checking plus those causing hardware traps over all the injections. Latent is the percentage of the latents after injections over all the injections, and residual is the percentage of the wrong behaviors of the application without detections. The diagnostic coverage is the sum of the safe and the detected ones. In this slide are reported experimental data obtained from the experimental campaign considering an allotted fault tolerance time interval of 1000 instructions. In this graph it is possible to see that we have a diagnostic coverage of about 50%. Since of course this work deals with real-time embedded software, for the version compiled without compiler optimizations, it has also been assessed the diagnostic coverage when different fault tolerance time intervals were considered. So in particular we computed it considering an allotted time of 10, 100, 250, 500, 1000, 5000 and 10,000 machine instructions executed from the moment of the injection up to the detection. For the overheads, we consider two different aspects. The increase in size of the text memory segment that represents the increase of the number of instructions of which the application is composed of, and the increase of the number of executed instructions in the emulated scenarios, which impacts on the execution time, that is especially critical for real-time applications. We can see that while we have a strong increase in the text size segment, the increase of the execution time for the considered application is less than 20%. Of course, it is important to remark that this impact depends on how many basic block transitions happens, and so it's strongly application related. The source code and details on the experimental results are available on GitHub by following the QR code shown in this slide. We have, moreover, two planned future works. First, we would like to perform a back-to-back comparison on the same application written in C and Rust. This comparison will allow to further investigate how the control mechanisms implemented after the static analysis at compile time by Rust can hide the fault detection, of course, if any effect is actually present. As a second activity, we would like to publish guidelines on how to implement Yakka and Rackfed in Rust to allow interested scholars and engineers to replicate our result. Thank you for following this pre-recorded presentation. I look forward to meeting you from March the 31st in Lyon to answer your questions and discuss this topic together.